Everyone. The plan today is to start by finishing up one last rule that I didn't get a chance to do yesterday for the laws of logarithms, and that's the change of base formula. And you'll see what that is in a second. And then to do a whole bunch of examples of the different rules and combining all the rules together and seeing how all this kind of fits together. So I had asked if there were any questions regarding the homework, and I didn't get anything in chat. So I'm going to assume then that the homework was okay, and we will be going over quite a few of the same style of questions, just more complex today anyway, so that might help with that issue. And if, as always, you have any other questions about the homework, just email me which numbers, and I've helped a couple of students that way already, and I think it worked out pretty well. So just let me know. Okay. All right. So we are going to be looking, like I said, at the change of base formula to start today. And basically what I'm asking you is, and I know some people may already know this again, but I'm going to go through it step by step, okay? How would you solve to find for x? That's a redundant statement. How would you solve for x in this statement here? X is equal to log base 7 of 15. And I'm specifically saying without trial and error. So I want to get a perfect answer from a calculator, okay? The issue is that your calculator, now this is funny, some newer calculators actually do have the ability to change the base of the logarithm. So I'm not sure if eventually this lesson is going to become pointless, but for now, it's always important to know where this stuff comes from anyway, okay? So even if calculators will eventually be able to do this kind of thing, I want you to understand how it works, all right? So the calculator does not have a log base 7 normally button, okay? The only two logarithms on a calculator are the log button and the ln or ln button. Okay, so let me write that in here. Calculators usually only have a log button, which actually means log base 10, or an ln, I'm going to write the L this way so it doesn't look like an I, which means log base E. There was a fantastic video on Numberphile recently about E. So if you search Numberphile and E on YouTube and watch that video, unfortunately it's British. I shouldn't say unfortunately. They use the pound symbol for money in that video, but it's still pretty understandable anyway. And they explain everything. So I'm not going to go into E because that's actually a calculus idea, and I don't want to steal all of those teachers' thunder for next year. So, but you can look it up if you're interested. So ln is a type of logarithm, and log is the main logarithm that we usually use, although eventually ln will become the more preferred one. And those are the only two logarithm buttons on your calculator. So how do you do a log base 7? Well, we do that by doing what's called a change of base. We're going to change our log base 7 into a log base 10. And the way we do that is by first rewriting this as an exponential. Okay? So, and eventually you won't have to do all these steps. Eventually you'll just be able to jump right to the final answer. But for now, I'm going to show you all the steps, like I said. So how do we change this into an exponential? Well, we talked about yesterday how we use inverse functions to destroy functions, right? So, and I showed you a quick little trick. When you're trying to go from a logarithm to an exponential, if I put, so I'm looking at the base 7 here. If I put a big 7 here and a big 7 here, basically what I've done is I've raised the x up as an exponent, and I've raised the log base 715 as an exponent, okay? And that's how you destroy a logarithm, is you raise them both up into the exponent position, or the power position, and then that eliminates, it destroys the logarithm on the right hand side. So what we end up with then is 7 to the power of x is equal to just 15. okay? And we could use trial and error here to try to solve that, but I don't want trial and error. So what we're going to do next is we're going to use the down in front law that I showed yesterday, and it was the last proof that I showed yesterday, and we had been using it a couple of days ago as well, with one of the calculator logs. So I'm kind of repeating what I said up here about which logarithms to use. Log, which is log base 10, or ln, okay? So you can use either one of those two logarithms at this point. We're going to use log base 10 though. So let me just check something. I can't remember if I continue this. Okay, I think I can continue right on this screen. So, you know what? Just to save me some room here, I am going to switch screens. So I'm just going to copy this and go over to the next slide. So let's log base 10 both sides. All right. So I'm going to put a log base 10 on this side. I'm going to put a log base 10 on this side. Everything else stays the same. All right. And what that does is allows me to bring that x down in front. And remember, that's what we're trying to solve for. Actually, I'll go to another color here. Okay, so we changed it to an exponential. We log both sides, and you could have used ln here, ln, the natural logarithm instead. It doesn't matter. Both of them bring the x down in front, and then we divide the ln 10(7) over to the other side to get x all by itself, because that's just a multiplication. Okay. Now, what I would like you to do is compare that to our original, which was x is equal to log base 7 of 15. How did we convert this into that? What shortcut could we use? Well, if you notice, the 15, which was inside the log, is just at the top of the fraction, and the 7, which is the base of the log, is the inner value of the logarithm at the bottom of the fraction. So in general, that's the trick that we can use each time. And I believe it was just put in chat, although in chat there was a logarithm and then a ln put in at the same time, which is okay. It has to be all one or the other, okay? So in general, if you have log base a of b, you can turn that into, how do we write this? Just regular log of b over log of a. Actually, I just realized the chat statement is correct, because this logarithm could be anything, either log or ln. Okay, either of those two, I should say. So log base a of b is equal to log of b. So you take what the base is, what the b value is, and you put it at the top of the fraction inside of a logarithm, and what the base is, and put it at the bottom value of the logarithm. Okay. You know what? I don't like that. I know that's the way it is in the book, but I mentioned the other day that I don't like writing a for base. So I'm going to switch this around if that's okay. The base goes at the bottom, the inner value of the logarithm goes at the top. And I think in the textbook it's actually written as a base of a. I don't like that convention, so I'm changing the rules. Okay. So if we finish this one off, log base 10 of 15, log base 10 of 7, you can actually type all of that into a calculator. So I'm going to pull up the calculator here. So let me just delete that entry. So on this calculator, I have to put the number in before I press the log button. So 15 log divided by 7 log and equals, and the answer would be 1.39, and there's a heck of a lot of precision to that answer, okay? So I'll go back to my smartboard. So 1.39 would be the answer with all of the precision that we would need, okay? So I'll just put an approximately equal there. And that's really the last rule that you need to know to do any logarithm question. So if you're asked to find the solution to a logarithm and you don't have a calculator that can change the base, you can just switch the base yourself by following this pattern. Let me highlight that pattern. Right here. Okay. So if you don't mind, I'm not going to do any more examples of this because I think some of those examples are coming up later. But before I move on, is there anything you need me to explain more in detail about how this change of base formula works? Seeing no comments in chat, I'm going to assume that that's okay. And like I said, we will do some more examples of it later anyway. So let's take a look at combining some of the logarithm laws. And I'm actually going to start with a question that might be a little bit difficult depending on how well you know the relationship between roots and powers. So I actually just scanned or took a snapshot of questions directly out of the grade 12 calculus book that you were doing your homework from yesterday. I'm not going to do all of these questions. I'm just going to do one or two, depending on how much you feel like you might need me to do some more. But there's an aside that we have to do here, and we've talked about this before. Oh, let me delete that. So we're going to just do a little aside here before we start looking at these questions. And I don't know if you've seen this before, but there is a way of writing roots. So let's say this was a square root, which would be a 2 here. There is a corollary or another way that we can write a root as an exponent. And we haven't done the exponent law review section yet. We are going to do that later. And I don't mind having done this first and that later, okay? Because it's the idea of revisiting concepts that we've already seen, which helps the brain usually really understand and remember those concepts. There's a way of changing a root into a power. In chat, I wonder if anybody could answer the question, what power would replace that root? And the other question I'd have is how many of you have seen it? Okay, because I know that you see the power rules in grade 9, and I don't know how far the teacher in grade 9 would have gone. So there's a couple of you that have seen this. Is there anybody that hasn't seen that becomes a 1/2 power? Power rules in grade 9, negative in grade 10. Negative powers, you mean? So they don't do fractional exponents in grade 10. Okay. So then I'm going to ask those of you who understand this very well to be patient here, because I am going to go through a brief little lesson as to how this makes sense. Okay? And the brief little lesson is basically just pulling out your calculator and doing the following. What does 9 to the 1/2 give? So I may end up needing a little bit more room here. But what does 9 to the 1/2 give on a calculator? Well, you can type that in as 9 to the 0.5. And if you do that on a calculator, you're going to get 3. Okay? What does 16 to the 1/2 give? Well, 16 to the 1/2, again, 16 to the 0.5, will give 4. If you do 8 to the 1/3, you will get 2. And what you start to notice is for this side, these are behaving exactly like square roots. These are behaving exactly like cube roots. Okay? So that behaves like a square root. That behaves like a cube root. Therefore, these are roots. Okay? Fractional exponents are roots. So you can change any root into a fractional exponent, and the rule is that the denominator of the fraction, let me highlight that, the denominator of the fraction is the type of root that you're dealing with. So over here, the denominator of the fraction would be the type of root. Now with a square root, the word square is right in the word square root. Okay, square usually means power of 2. So a square root, even though there's no symbol here, and I mean, here's some of those things that make math difficult for people who have trouble grasping some of the concepts. When you don't have a value, how many times is that replaced by a 1? Right? Why is it all of a sudden replaced by a 2 here? And it's because of the name square root. But those kinds of things will mess people up. Like I've had students mess up oftentimes when there's no number there. Is it a 1 or is it a 0? Well, it depends, right? It depends. If you're multiplying by a quantity and there's no number there, that number is considered to be a 1. But if you're adding a quantity or subtracting a quantity and there's no quantity there, then the number is assumed to be a 0. So there's a lot of little tricky things like that in math. Anyway, as a teacher, I've noticed throughout the years that those are the kinds of things that throw people off. Anyhow, sorry, I get long-winded sometimes. My whole point is that when you have a root, you can rewrite a root as a power. Now, how is that going to help us for those questions up there? Now, there's one thing I'm going to have to do here because I ran out of room by explaining all that. I'm just going to add a page, and I'm going to switch to my mouse for a second because I'll be able to do this quicker with my mouse. I'm going to move this picture to the next slide to get it out of our way. For now. And let's get back to these ones. Okay, so that whole aside was just to explain that any root can be written as a fractional exponent, okay? So let's get back to 4a. In 4a, the question is, evaluate using the laws for logarithms of powers. So log base 3 of cube root of 9. Oops. So log base 3 of the cube root of 9. Well, we didn't see any laws that deal with roots yesterday, but we did see laws that dealt with powers. So I can rewrite this as log base 3 of 9 to the 1/3 now. Using what I just showed you in the aside up here, I can change this root 3 into a power of 1/3. Now, how does that help us? Well, what is the law that deals with powers? When you have a power in that position, you can bring that power down in front. As a multiplication. So that power is no longer affecting us, which means the root is no longer affecting us. Can we do log base 3 of 9? Well, using the little trick I showed you yesterday, if I pretend there's a little power right here, 3 to the power of what equals 9? Everybody should be able to answer that. So the 1/3 stays there. 3 to the power of what equals 9? That's 2. Multiply those two together, which is where I'm worried that some of you may mistakenly do the wrong thing, because multiplying a fraction times a number messes people up all the time. It's top times top, bottom times bottom. The answer is 2/3. And we've now solved that question. And if we go back up and look at all of the other ones that deal with roots, okay? Like, let's look at B. This would become a 27 to the 1/4. Let's see if we could do this in our brains without writing anything down. This would become a 27 to the 1/4. The 1/4 would move down in front. We'd have 3, log base 3 of 27. Well, 3 to the what equals 27. 3 to the 3 equals 27. So the answer to the logarithm without the root is just 3. And we've got 1/4 in front. So that's 3/4. I don't know if you were able to follow all of that, but we were just able to answer that question without writing anything down. Okay? How quickly could you come up with this answer? Go! Answer in chat. How fast can you come up with this answer? Well, we've got one right answer. The answer is 2/3. Okay? So think about it. It's going to become 36 to the power of 1/3. The 1/3 comes down in front. So keep that 1/3 in your brain. Now we've got 6 to the power of something that has to equal 36. 6 to the power of 2 is 36. So the answer to the logarithm without the root is 2. And we've got that 1/3 in front. 2/3 is the answer. That's okay. Mistakes are fine. Do you know how to do it now, though, is the question. Do you understand where you made your mistake and how to fix that problem? Okay? And I'm asking you to do it fast, which is never fun. I'm not good. I'm glad you figured it out. So speed, I have a lot of people say math shouldn't be about speed, but it will become about speed if you have a question that takes you 3 hours to answer, okay? So you do need to get confident with what you're doing. So let's do D, okay? Now this is a square root, so that's a 1/2 power. 1/2. 5 to the what is 125? How fast can you do that? If it's 1/2 and that answer, what's the final answer? Awesome. Some of you are getting it very quickly now, okay? So as hard as these questions may have looked, I'm hoping that they're not as difficult anymore, okay? Just understanding this little trick that you can do with a root and starting to really understand what a logarithm is, that it's just a power that the base has to be raised to give the number that's in the logarithm. And this should not be hopefully a difficult concept anymore. Now this one's interesting. I don't know why they threw this one in here. It is a power, right? But it's not a root. So remember what we do with fractions? We flip them upside down, right? So that becomes 16 to the -1. So that -1 comes down in front. 4 to the what gives 16? It's 4 to the 2, but -1 times 2. So the answer would be, yeah, flip them, exactly. So if you flip this one, the -1 comes down in front. The answer would be -2 here, okay? So we don't even have to, if you're able to follow that, that's fantastic. If you're not, some people do need to write the math down. Even myself, sometimes I have to write the math down. But, just challenging yourself to do some of these in your head sometimes, it makes, I'm snapping my fingers here, it makes things go a little bit faster and can be a little bit more exciting. Okay. I'm going to move on, if that's all right. So let's take a look at these folks. Evaluate and then state the logarithmic law that you used. So yesterday you were dealing with a lot of just addition of logs or subtraction of logs and the power law all separate. But you can actually chain those laws together. You've got to follow the order that they kind of show up in. Okay, there's a little bit of bedmass going on here. But let's take a look at 5a together. Now the first thing I want you to notice, oh, my technology just died on me. Oh no! Oh, it's back, it's back. Okay. Don't know what happened there. Log base a of 6 minus log base a. Log base 8. Okay. So, first thing I want you to notice is all of them are log base 8. That's important. You can't join two logarithms together if they have two different bases. Okay? So we're going to join these two together first, and I'm going to do. You can do it all in one step, but I'm going to do it a step at a time. What is the law when we're subtracting? So somebody throw in chat. What do we do with the 6 and the 3 when there's a subtraction between the two logarithms? That is correct. So we're going to divide 6 divided by 3. So the whole point here is to try to get everything under one logarithm. Okay? Now what, and I know you know that 6 divided by 3 is 2, okay? But I want to try to lead you towards being able to do this all in one step. So what would happen now when we have these two together? Well, what does an addition become? An addition becomes a multiplication, right? So you could have skipped that middle step and gone directly to this. And yes, you could have done the 6 divided by 3 in your head, but if you want to show all of the steps, that's the way it would look, okay? So now we know that the answer is going to be log base 8 of 4, right? Now, what did they say? They said evaluate and then state the logarithmic law that you used. So we've got log base 8 of 4. Somebody got an answer really quickly there. 8 to the what equals 4. Now, unless I'm, yes, okay. Unless I'm missing something, there's no way of directly getting to the final answer, okay? So this is one of those cases, because they said evaluate, if I put an X here, we need now, so what laws did we use? We used the subtraction law, we used the addition law, but we need one more law to be able to evaluate this, and that law is the change of base. There is what? There is a way to get it from 8 to 4 easily? What am I missing? Okay, I'm going to show the change of base method. If you can explain to me what I'm missing. Ah, all right. Interesting. Okay. I'm not sure how many people would catch on to that one quickly, so let's do the full change of base idea. You know, just in case there may be scenarios later on where this will not be possible. I mean, if this had been 4.73 or something like that, then I don't think you would have wanted to try to do it mentally. So let's just do the change of base and show you where the change of base comes into play. So if you remember, the change of base allows us to change any logarithm into any logarithm we want, and we want base 10, so just a log. So we're going to do log 4, following the pattern from before, divided by log 8. And then that should give us our answer that we were looking for. Okay? Which I'll let you do on your calculators on your own time. So the idea here is how many different rules did we use to find the answer? And if you look at each and every one of the other questions, except for the ones B, D, and F, well, we just did those. okay? So I'm not going to do those again. But if you look at A, C, and E, now I think I'm going to do E with you because E has these scenarios, all right? So let's just talk about how do we do those scenarios. So I'm going to extend down here, and I've already forgotten what they were. So log base 8, 2. 3 log base 8, 2. Oh, and they're throwing a curveball at me there. And 1/2 log base 8, 16. Okay, so we want to combine all of these together, all right? The problem is, with this one specifically, it's log base 8, 16, and I'm trying to join it with a log base 8, 2, and I can't do that, okay? And the 3 and the 1/2 in front of these two logarithms are getting in the way as well. Now, there is something special we can do with these two. This is the curveball I was just talking about. It's not the way I wanted to solve it because I wanted to show you how to deal with the 3 in front of the log base 8. But can anybody see what we can do here instead of using the logarithm law right away? What's log base 8, 2 plus 3 log base 8, 2? That's right. It's like 1x squared plus 2x plus 3x squared is 4x squared. So you can actually just join those two together because they both have the same logarithm base, which is probably the easiest thing to do for those two right now. So let's do that. There is another way that we could have worked with that, but I think that is the best way to do it, okay? So if you notice that your logarithms have the same base and the same inner value, then you can actually just add them together, okay? But they have to have those two things in common. Same base of 8 and same inner value of 2. I cannot join these two in the same way because their base of, so the inner value is 2 and the inner value is 16. All right, but I still do want to join them all into one logarithm. Well, what do I do with this 4 in front? And this is, I think, the first time you're seeing this with me. We're going to do the reverse down in front rule, okay? We're actually going to move this 4 up to the power position over here. So we're going to get log base 8 of 2 to the 4 plus, and we're going to do the same thing with this 1/2. We're actually going to do the reverse. So I'm going to write that off to the side here. Reverse the down in front rule, which I used to jokingly call the up and back rule in class. So we're going to bring that power of 1/2 back up to the exponent position. Well, that is going to allow me to actually do 2 to the power of 4. And what is 16 to the 1/2? Well, we just recently saw that 16 to the 1/2 is actually just a square root. So what's the square root of 16? It's just 4. So let me pause there for a second, okay? With numbers in front of the logarithm, sometimes you can use what I jokingly call the up and back rule. Instead of using the down and front rule, let's move them up and back up here so that now we can actually use our logarithm rule. See, we can't combine the plus up here sorry, let me rephrase that. The plus up here we can't use to combine the two logarithms because they're not in the proper format yet to use the addition rule. The addition rule can't have numbers in front of the logarithm. So you can't have a 4 in front and you can't have a 1/2 in front if you're trying to use the addition rule. So let's get rid of the 4 by bringing it up and back. Let's get rid of the 1/2 by bringing it up and back. And in this case, they just, simplify rather easily anyway. And now we've got 40 plus 24 to multiply 4 and 16, which I believe is 64. And 8 to the what? So using my trick at this point, 8 to the what is 64? Well, the answer is 2. 8 to the power of 2 is 64. And your worlds have now gotten a lot bigger mathematically. You can solve some very interesting questions at this point. Are there any... Yes, it absolutely is beautiful. I agree. Are there any questions about that? And having seen those two examples, do you think you could try to tackle C? Yes, there are other ways that we could have done this, for sure. Like what I was thinking of doing is I could have brought the 3 up here, right at the beginning. And that would have been 2 to the power of 3, which would have been 8. Okay, there's other things we could have done here. But anyway, play as much as you want. Just use the rules correctly. Okay? No cheating. All right. How about these ones? So this is saying express each expression as a single logarithm. It's not even asking us to solve them. Okay? Do you see how doing the previous slide has basically solved any problems we might have with this one? Could you do 6a? And I'm going to answer for you. I believe you could at this point. Okay? I'll explain the 3 in front of the log, up and back. Both of them would now be log base 5. Use the multiplication rule to combine them. Sorry, folks, I'm getting hiccups here. I'm just blocking my microphone so you don't hear the hiccups. Whew. Yeah, so could you simplify all of that stuff now? I am going to leave those, and I will be posting the homework questions to the Google Classroom. And again, do as many as you need to master them. But I'm hoping that if you look through these now, they do not look nearly as scary anymore. Okay, so I'm not going to do any of those. Let's talk about these ones. So these ones are a little bit weird because they have a logarithm on both sides and the x is inside the logarithm. Now, I'm going to explain this by doing one of them with you, okay? There's one more rule that I didn't talk about, but it's technically not even a rule because it's a logical, what am I trying to say? Result to what we're about to see, okay? So all I'm going to do is I'm going to leave the log base 2 of x on this side alone for a minute. But I am going to work on this part, all right? Well, that part is an addition, so we know how to deal with additions. It's just a multiplication. So 5 times 10, right? So I end up with log base 2 of x equals log base 2 of 50. Here's the rule. And I'm going to draw it out. Here's my dragon again. But this time the dragon has swallowed the sheep. Here's my dragon again. Wow, my art skills are great. Oh, you know what? I made one little mistake, sorry. Let's move the sheep to that dragon. Yes, I'm having fun. Okay? If the dragon has swallowed a sheep, and it's the same dragon that has an X in its stomach on this side, what does X have to equal? X has to equal the sheep. That's the rule. Okay? So if you have log base 2 of X on this side, and you have log base 2 of 50 on this side, what does X have to equal? You just drop the logarithms. It's very, very similar to the drop the base rule that we were doing the other day for exponents, because logarithms are exponents. Okay? So that's the only thing new about that particular set of questions. Each one of them is set up the same way. You'll notice that the bases, like for B, it's all base 3. For C, it's all base 10, right? They're just plain logarithms. For D, it's all base 10. For E, it's all base 5s. Now with E, the only thing that's tricky is they have this log base 5 of 8. Where is it going to go? What am I going to do to this log base 5 of 8 to be able to solve E? Correct. We're just going to move it over to the right-hand side and join it with all of those logarithms. Okay? So, again, pat yourselves on the back, folks, if you're even able to understand a little bit of what I was just saying there. Like, these, you throw some of these questions at any person who's just started to learn logarithms, and they're going to panic. But at this point, you should have a much better understanding of how all this works. Like, if you look at a 2 log 4, the 2 goes up to the top because we're going to have to join that. The 3 goes up to the top. Like, I'm hoping that that's happening now. And if it isn't, please let me know in email so that I can help you out a little bit. Is this part of it's part of the IB curriculum. So it isn't part of the regular grade 11 curriculum. This is a grade 12 calculus concept. Or sorry, advanced functions concept. You're right. It comes out of the calculus textbook, but it's advanced functions and calculus usually. So it's part of the IB. If the log bases are different, you sometimes cannot solve the question without using graphs. And to tell you the honest truth right now, I don't remember algebraically what you do. So there are possibilities, like just as an example, and remember, logarithms and exponents are corollaries of each other. They're very, very similar in rules, right? How would you solve that? There's no other way besides doing 3 to the 5 separately, 4 to the 7 separately, and then multiplying the two together. Okay? So I'm having trouble thinking of a logarithmic example of that right now, and please don't put the stress on me to try to figure one out right now. But as far as I know, like what you might have to do, actually, I'm just thinking of something here, and I might be completely off. I'm sure somebody will correct me if I am. If you had log base 3 of 4 plus log base 5 of 7, for instance, you could use a change of base formula to change both of these to a log of base 10. Or you could change one of them into the other logarithm, right? So we have that change of base formula now that would allow us to change one of the logarithms into the other type of logarithm, or both of them into a log base 10. And I think that's what you'd have to do. But that's right off the top of my head without like reviewing notes. Okay? So I'm pretty sure that's what we'd have to do in a case like that. So I'm going to erase that from the note because that's a much more advanced question. And I have one more. That sounds right? Okay. Yeah, thank you for the backup. You know, I'm a math teacher, but they say that the best mathematician in the world only knows 1/10 of all the math that's out there. There's a lot of things that I have to remember, and when you put me on the spot like that, sometimes I may not remember, but I'm pretty sure that's the correct process for that. So forgive me if I'm not infallible. Take a look at this one. Now, chat, please don't answer it right away, okay? because I want everybody to think about it, and if you throw the answer up there, it might throw people off. So if I could ask you to hold off, if you know the answer, please let me guide everybody through it first, okay? So I want everybody to think about this one. And to get us moving along here, now this you can answer. How would we combine those two logarithms if it's an addition? Correct. What would that multiplication look like? Aha! This is a quadratic. This becomes log of x squared minus 7x. Okay, again, please don't answer the next step. I want everybody to think about what the next step would be. How would I now get rid of the logarithm on the left-hand side? So don't answer, please. Everybody just think about it. Okay, now you can answer. How do I get rid of the log on the left-hand side? What am I going to have to do to both sides to get rid of that logarithm? You got it. We've got to change this to exponential form. Now, how do we do that? So remember the trick? That's right. We're going to put a big 10 here. We're going to put a big 10 here. Okay? And I'm going to warn everybody, I was doing this in my head yesterday. If I didn't make it factorable, I'm going to be very upset. So somebody out there in chat land, check to make sure that the answer is going to be factorable here. Okay? All right. What does this 10 to the log do? This is an inverse function of a function. Whew, thank you. This is an inverse function of a function. An inverse function of a function kills the function and pulls out the argument, which in this case is x squared minus 7x. On this side, we have 10 to... don't do that to me. Did I forget because the... So, okay. We'll make it work if it doesn't. With one, hopefully just one simple little change, okay? This is what might have messed me up. How do we get this to be a regular quadratic now? And you're right. It won't be factorial. Oh! I'm very upset with myself right now. Okay, you know what? I don't care if it's not factorable. We can still solve this. We're going to make it a grade 11 IB question. We can still solve this. Why is it not factorable? Because I thought that was going to be a positive 10. Can we find two numbers that multiply to negative 10 and add to negative 7? I was hoping it was going to be negative 5 and negative 2, but it doesn't work. Well, what do we do with a quadratic if it doesn't work? So let me pause here because I'm upset with myself. The fun thing about this question is the fact that it's quadratic. It's a logarithm, but it's quadratic. Okay? That's the fun thing about it. I was hoping that I was going to be able to figure it out in my head that it was going to be factorable. I should have tried it on paper. I forgot that when this moved over to here, it becomes a negative 10. So what? If we can't factor, what do we do, folks? Yeah. So let's do our discriminant. We are going to use the quadratic formula, so we're going to find our discriminant. So we've got b squared, which is minus 7 squared, minus 4 times a, which is 1, times c, which is negative 10. Complete the square. We're not going to complete the square to find zeros. That is not the most efficient way. That becomes plus 40, if I'm not mistaken. And that becomes, 89. So please double check my math there. I think I did that right. Stop. Why am I stopping? Bolt. Oh, okay. You weren't talking to me. All right. When I see a big stop like that, I figured I'm going too fast. So, just to quickly recap, we had a logarithm scenario. We multiplied the two inner parts of the logarithm because of the law of addition. We got a quadratic. We raised both sides to the base of 10 to get rid of the logarithm. That gives us a quadratic, which unfortunately is not factorable. However, our discriminant tells us that there are two zeros because it is a positive answer. Okay? I'm going to let you folks finish this one off. Completing this... Okay. Completing the square might be epic, but it's the worst choice to find zeros. And the whole reason it's the worst choice is because of the proof of the quadratic formula that I gave you in class before holidays. The proof of the quadratic formula uses completing the square, but ends up with the quadratic formula to find the zeros. Okay? So that's the whole reason why we don't use the quadratic formula. Sorry, that we don't use completing the square to find zeros. Because the proof of the quadratic formula shows that we don't need to. All right? So when you're finding zeros, and we can argue this in person, with boxing gloves if needed, that this is the proper way to find zeros. Okay? Yes. I will get fired up about that. All right? So yes, I'm going to let you finish this one off, folks. It's just plugging it into the rest of the quadratic formula now, which I hope everybody has memorized at this point. And that finishes the unit. Finishes the unit. Somebody's going to clip that. Sorry. It finishes the unit, except we didn't do graphing logarithms and the transformations of logarithms. Yeah, that was a pretty quick unit, I know. Now, technically, we're supposed to do the finance unit right after this one, which is actually still part of this unit. I'm actually getting worried that if I keep this pace, that I may end up running out of material if we end up going all the way till May and even further than that. So I'm not sure what we're going to do about that. But I think we'll be okay. It wouldn't be a bad thing to have to slow things down a bit, but I mean, if we finish earlier, I could always start teaching advanced functions if I have to. But again, that would ruin things for next year's teacher. And it would ruin things for those of you who are watching and those of you who are not watching. So, because we're at 28 viewers. So we've actually dropped in viewers a little bit. Just make some stuff up we might not know. Yeah. I'm not so sure I want to do that. But, I mean, if it's okay with parents, we could always take a couple of days off here and there and let you concentrate on some of your other classes. Now, we'll have to see what happens. Like next week, we're going to be starting the more regular schedule. Okay? But let me worry about the timing. Okay? And I'll get back to you on that. So we're done this unit. Except for graphing logarithms. Now, for graphing logarithms, folks, just if I can talk about that for a second. Basically, the idea is if I asked you to graph a transformation of a logarithm, like y is equal to log of x plus log base 3 of x plus 4. What you would do, as always, is you have to find your base function's key points. Now, the base function of log base 3 would be found by doing 3 to the power of x's key points and switching the x's and y's. and then you just do the regular transformations like you would normally do. That's the only thing that's different. Okay, so because log base, whatever the base of the logarithm is, so if you have log base 5 in a transformation, you would use 5 to the power of x as its inverse function's corollary, and just invert the x and y values, and then you do all the transformations to those points. So I'm not going to teach that just to, I know I'm saving time because I actually was worried about running out of time, but I'm starting to think that might not be the case. If we ever need to review, that would be something that I could do at the end. If I ever have to do extra stuff, we could always come back to some of the stuff that I didn't get a chance of hitting. Yeah, so I'm going to say bye to stop recording.